Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A particular kind of intellectual pressure builds within a scientific tradition that has achieved maturity. The grand foundational paradigms have been established, the revolutionary insights have been articulated, and the core theoretical structures stand as magnificent monuments to generations of inquiry. The challenge then becomes one of immense subtlety. It is the pressure of precision, the demand for a perfect, frictionless alignment between an elegant theory and the unyielding facts of observation. By the latter half of the 16th century, the Kerala school of astronomy and mathematics had reached this very point. For over 200 years, it had flourished as a vibrant, self-contained universe of intellectual innovation, a lineage of masters and disciples building upon one another's work in an unbroken chain of transmission. The geocentric planetary models of Achyuta, which formed the bedrock of Indian astronomy, had been profoundly transformed by Kerala masters like Madhava of Sajgamagrama and Nalaka Insya Somayazya. They had developed what was in essence a geo-heliocentric system and armed it with a mathematical engine of unprecedented power, including infinite series expansions for trigonometric functions, the very heart of calculus, discovered centuries before its European formulation. Yet, this very success created a new, more refined problem. The school's own observational programs, carried out with meticulous care over decades, were yielding data of increasing accuracy, and this data revealed minute, yet persistent, discrepancies. The predicted positions of the planets, calculated using the sophisticated models of Nalaka, while astonishingly good, still deviated from their observed positions by small, nagging amounts. These were errors on the order of arc-minutes, tiny fractions of a degree. To an outside observer, this might seem like a trivial concern, a testament to the system's overwhelming success. Within the Kerala tradition, however, whose ultimate aim was Dikgekya, the complete agreement between computation and observation, these tiny errors were a profound intellectual challenge. They signaled that the grand synthesis, while brilliant, was incomplete. The theoretical edifice required a final, masterful adjustment. It needed a mind capable of grasping the entirety of the tradition, from its philosophical underpinnings to its most intricate computational algorithms, and possessed of the insight to identify the source of these last stubborn deviations. Emerging into this environment of high intellectual stakes was Achyuta Pisharati. Born around the year 1550 in the village of Trikandiya in present-day Kerala, he belonged to the Pisharati community, a group traditionally associated with temple services and, crucially, with classical scholarship. His life and work represent the culmination of the Kerala school's golden age, a period characterized by the synthesis and perfection of earlier discoveries. His career was a demonstration that the final act of a scientific revolution is often performed by a figure of immense erudition and synthetic genius, one who organizes and refines the breakthroughs of their predecessors into a coherent, practical, and supremely accurate whole. Pisharati's intellectual pedigree was impeccable. His primary guru was the great Jayas Himhideva, a monumental figure in his own right. Jayas Himhideva was the author of the Yuktibhashya, or rationale in the Malayalam language, a text unique in the history of world mathematics. The Yuktibhashya was a complete exposition of the mathematical and astronomical discoveries of the Kerala school, providing detailed proofs and logical derivations for everything from the infinite series for sine, cosine, and arctangent to the algorithms for calculating planetary longitudes. To be the direct disciple of Jayas Himhideva meant that Achyuta Pisharati received his education at the very source of the tradition's most advanced knowledge. This was a tutelage that went far beyond the rote memorization of formulas. It was an immersion in the deep structure of mathematical reasoning, an apprenticeship in the art of the proof, and a direct transmission of the intellectual spirit that had given birth to Indian calculus. This training shaped Pisharati into a formidable scholar who soon became a celebrated guru himself, establishing his own school and attracting brilliant students. Perhaps the most famous of these was Melpathur Narayana Bhattathiri, a towering figure of Sanskrit literature and devotional poetry. The relationship between Pisharati, the astronomer, and Bhattathiri, the poet-grammarian, illuminates the intellectual ecosystem of the time. Scholarship was an integrated enterprise where mastery in one domain commanded respect across all others. Pisharati's role as a teacher was central to his identity and his influence, ensuring that the sophisticated knowledge he inherited and refined would be passed to the next generation. His intellectual pursuits, moreover, extended into fields that a modern perspective might view as separate from mathematics. Pisharati was a distinguished grammarian, a master of the complex and highly formalized system of Sanskrit grammar, or Vyakara. He composed a celebrated commentary, the Prakashika, on a grammatical text known as the Kriyakrama. This work on the structure of verbs and sentences is a testament to his command over the classical Indian scholarly apparatus. For Pisharati and his contemporaries, this was a vital skill. The study of grammar trained the mind in a particular form of analytical rigor. It demanded the precise application of rules, the resolution of apparent contradictions in foundational texts, and the construction of logically airtight arguments. It was a discipline of pure structure. This same intellectual musculature, developed through the meticulous dissection of language, was precisely what was required to dissect the complex motions of the heavens. His deep engagement with grammar provided him with the mental tools for logical clarity and systematic exposition, qualities that would become the hallmark of his astronomical works. He approached the problems of planetary astronomy with the same expectation of internal consistency and logical coherence that a grammarian brings to a foundational text. Therefore, when Achyuta Pisharati turned his full attention to the outstanding problem of his day, the final reconciliation of theory and observation in astronomy, he did so as a complete scholar. He was a mathematician steeped in the analytical methods of his forebears, an astronomer familiar with the long history of Indian observational practice, and a philologist trained in the rigorous interpretation of complex systems. He embodied the synthetic impulse of his era. The task before him was immense: to scrutinize the entire computational system inherited from Nilaka, Inchra, identify the subtle sources of error, and devise new corrections and methods that would close the gap between the calculated and the seen. This endeavor would require him to produce a work of supreme clarity and computational elegance, a treatise that would serve as the definitive statement of the Kerala school's astronomical system. He would need to create a text that was both a theoretical masterpiece and a practical manual, a tool for future astronomers to use in their quest for perfect prediction. This monumental undertaking would result in his masterwork, a text designed to achieve a new, unparalleled standard of precision in determining the true positions of the planets. The Sphutine Nirnaya, completed around the year 1601, stands as the magnificent culmination of this quest for precision. The very title, translating to the determination of the true, announces its ambitious purpose to establish a definitive method for calculating the true longitudinal positions of the planets. It is a work of immense intellectual density, composed in the traditional Sanskrit verse form, yet accompanied by a lucid prose commentary, likely penned by Pisharati himself, that illuminates every intricate step of his reasoning. This dual structure made the treatise both a memorable piece of scholarship and an exceptionally clear instructional guide. The challenge Pisharati confronted was one of subtle yet persistent error. The astronomical models he inherited, including the sophisticated geo-heliocentric system of his predecessor, Nilaka, Niha, Somayaju, were remarkably effective. They could predict planetary positions with a high degree of accuracy. However, for a mind like Pisharati's, a high degree was insufficient. Small discrepancies, measured in mere arc-minutes, still lingered between the positions yielded by the formulas and the positions observed in the heavens. For the casual observer, such a tiny deviation is imperceptible. For the dedicated astronomer, it is a chasm separating theory from reality, a constant whisper of an incomplete understanding. The Sphutinernia was Pisharati's grand attempt to silence that whisper. His first major refinement addressed the very heart of planetary computation, the complex relationship between a planet's mean motion and its true observable motion. Ancient astronomy understood that planets speed up and slow down in their orbits. The mathematical procedure for correcting the average position to find the true one, known in Indian astronomy as the Mandaphala, or equation of center, was the central operation. Previous methods provided a good first approximation. Pisharati, seeking a higher order of accuracy, implemented and perfected a powerful iterative technique. The method is a model of computational elegance. An astronomer would begin with the planet's mean longitude, a value easily calculated from tables. From this, a first correction term would be derived using sine tables and the parameters of the planet's orbit. This correction, when applied to the mean longitude, yields a first approximation of the true longitude. Here is where Pisharati's refinement becomes crucial. He recognized that this first approximation was itself a better basis for calculation than the original mean longitude. The astronomer was instructed to take this new, more accurate position and use it to recalculate the correction term. This second correction would be slightly different and more precise than the first. Applying it would yield a second, even better approximation of the true longitude. This process could be repeated, with each cycle producing a value that converged ever closer to the planet's actual position. After 2 or 3 iterations, the change in the value would become vanishingly small, indicating that the solution had stabilized and a state of high precision had been achieved. This method of successive approximations is a profound insight, prefiguring the logic of numerical methods that form the bedrock of modern scientific computing. It demonstrates a deep, intuitive grasp of how to systematically reduce error and converge upon a correct solution when a direct algebraic formula is intractable. This powerful iterative engine was then aimed at an even more subtle source of astronomical error, leading to Pisharati's most celebrated contribution. His analysis revealed that a fundamental geometric assumption in prior models needed correction. The primary reference frame for celestial mapping has always been the ecliptic, the great circle traced by the sun's apparent path through the sky. A planet's longitude is its position measured along this circle. However, the planets themselves travel in their own orbital planes, each tilted at a slight angle to the ecliptic. Previous computations, even highly sophisticated ones, would calculate a planet's position along its own tilted path, and then treat that value as its ecliptic longitude. This is akin to measuring distance along a winding mountain road and declaring it equal to the straight-line distance on a flat map. The difference may be small, but it is real, and it varies depending on where the planet is in its orbit. Pisharati was the first in the Indian tradition to systematically quantify and correct for this discrepancy. He introduced a new specific correction, which he termed the Udantara Sersha. The name, which translates roughly to the correction arising from the difference in rising times, points to its observational basis, but its mathematical function is a precise geometric transformation. It is what modern astronomy calls the reduction to the ecliptic. Pisharati developed the formulas to calculate the exact size of this correction. He showed that its magnitude was dependent on two factors: the planet's celestial latitude, meaning its angular distance above or below the ecliptic, and the planet's position along its orbit. The correction is 0 when the planet is crossing the ecliptic plane and reaches its maximum value when the planet is at its highest or lowest point relative to it. The effect of the Udayantara Sanskara was to take the planet's calculated position in its own orbital plane and project it perpendicularly onto the ecliptic plane, yielding a true ecliptic longitude of unparalleled accuracy. This was a monumental leap in computational rigor. It showed a mastery of three-dimensional spherical geometry and a relentless drive to model the physical reality of the solar system with the greatest possible fidelity. This correction, combined with his iterative method for solving the equation of center, endowed the system of the Sfruta-Nirnaya with a formidable predictive power. It became the definitive statement of the Kerala school's astronomical prowess, a theoretical monument built upon centuries of observation and mathematical innovation. The text itself, with its dense verses and clarifying prose, was a tool for the dedicated scholar, a guide to achieving a near-perfect correspondence between the world of numbers and the silent, wheeling cosmos. Its focus was on this abstract perfection, on refining the very language of celestial mechanics. The abstract perfection of a theoretical system finds its ultimate validation in the crucible of practice. An astronomical model, however elegant its internal mathematics, must eventually answer to the sky. It must predict where a planet will be when a festival should be held, and most demandingly, when the sun or moon will vanish from sight. Achyuta Pisharati's intellectual world extended from the highest planes of geometric theory to these essential tangible applications. His work reveals a profound understanding that knowledge gains its fullest meaning when it becomes a tool capable of shaping the daily and ritual life of a community. This commitment to utility gave rise to some of his most accessible and immediately impactful works, transforming the arcane calculations of the scholar into functional instruments for the working astronomer. This spirit of practical application is embodied in his manual, the Achyuta, a title that translates with a certain scholarly confidence as the best of handbooks. Within the tradition of Indian astronomy, a Achyuta text served a specific and vital purpose. It was a computational handbook, a vade-mecum designed for speed and efficiency, while grander treatises, the Siddhantas, laid out the foundational axioms and derived the complete mathematical architecture of the cosmos. A Achyuta text distilled this vast knowledge into a set of streamlined procedures. Pisharati recognized that the very sophistication of works like the Tantras, Graha, or his own Sfruta-Nirnaya made them cumbersome for routine calculations. The iterative methods and complex spherical trigonometry required for deriving a planet's true longitude from first principles were superfluous for a practitioner who simply needed to know the moon's position for a given evening. The Achyuta provided the necessary shortcuts. It established a specific epoch, a reference date from which all subsequent calculations would proceed. For this date, the text supplied the precise mean longitudes of the sun, moon, and the 5 visible planets, along with the positions of their apsides and nodes. These were the dhruvas, the fixed constants that anchored the entire system. From this secure base, the practitioner could use a set of simplified rules and pre-calculated tables provided in the text to determine planetary positions for any other day. The process involved calculating the number of days elapsed since the epoch, the Ahagasa, and then applying a series of corrections using Pisharati's concise formulas. This effectively packaged the results of the complex, underlying theory into a user-friendly format. The Achyuta allowed astronomers and astrologers to generate reliable results swiftly, making the advanced knowledge of the Kerala school a practical reality for a much broader audience. It was an act of intellectual translation, demonstrating Pisharati's genius as an educator as much as a theoretician. If the Achyuta streamlined routine astronomy, another of his works tackled its most dramatic and challenging application, the prediction of eclipses. His treatise, the Uparaga Kriya Krama, or Methodology of Eclipse Computation, represents a focused application of the Kerala school's full analytical power to this single, spectacular phenomenon. Predicting an eclipse with accuracy is the ultimate test of an astronomical system. The slightest error in the calculated position of the moon, the sun, or the parameters of the Earth's shadow can lead to a prediction that is off by critical minutes in timing or kilometers in location. For a solar eclipse, where the path of totality is a narrow band across the Earth's surface, precision is paramount. The Uparaga Kriya Krama confronts the core difficulties of eclipse prediction head-on. A central problem is lunar parallax, the apparent shift in the moon's position when viewed from different points on the Earth's surface. Because the moon is relatively close, an observer in the northern hemisphere sees it projected against a slightly different background of stars than an observer in the southern hemisphere. This effect, while present for all celestial bodies, is vastly more significant for the moon. Pisharati's work provided a refined methodology for calculating this parallax and correcting the moon's apparent position. This was a complex three-dimensional problem, requiring a sophisticated model of a spherical Earth and the observer's precise location upon it. The trigonometric tools honed by the Kerala school, including their advanced sine tables and geometric constructions, were deployed here to calculate the exact angular shift, ensuring that the predicted path of the moon's shadow in a solar eclipse would correspond to its actual path on the ground. Beyond parallax, the treatise addressed the crucial parameters of the celestial bodies themselves. The duration and magnitude of an eclipse depend directly on the apparent angular diameters of the sun and moon, and for a lunar eclipse, the diameter of the Earth's shadow cone at the distance of the moon's orbit. These values are dynamic. As the Earth and moon move in their elliptical orbits, their distances from each other and from the sun change, causing their apparent sizes in the sky to grow and shrink. The Uparaga Kriya Krama laid out improved methods for calculating these variable diameters with high precision. These calculations were directly informed by the superior orbital models developed within the Kerala school, the same models that underpinned the accuracy of the Sputana. A more accurate value for the eccentricity of the moon's orbit, for instance, translates directly into a more accurate prediction of its apparent size at any given moment, which in turn determines the length of time it takes to traverse the sun's disk or the Earth's shadow. Through the Uparaga Kriya Krama, Pisharati synthesized the theoretical advances of his tradition into a powerful predictive engine. The combination of accurate orbital mechanics, refined parallax corrections, and precise calculations for the variable diameters of the celestial bodies and the Earth's shadow yielded eclipse predictions of remarkable fidelity for his time. These practical manuals, the Achyuta and the Uparaga Kriya Krama, reveal a mind deeply concerned with the conveyance and application of knowledge. They demonstrate how the most profound mathematical insights become truly powerful when they are rendered into forms that can be used, tested, and relied upon. This act of making knowledge accessible and functional was a form of teaching in itself, a hint of the pedagogical role that would come to define his most lasting contribution. This impulse to distill and transmit complex knowledge found its ultimate expression in Achyuta Pisharati's role as a guru, a master teacher within the venerable Indian tradition of the Guru Shikha Parampara. This lineage of master and disciple was the primary conduit through which the most sophisticated intellectual currents of the subcontinent flowed. For a body of knowledge as intricate and demanding as the calculus-forged astronomy of the Kerala school, this intimate, personal mode of transmission was the very lifeblood of its survival. The challenge facing any great mind at the apex of a tradition is one of perpetuity, how to ensure that the accumulated wisdom of centuries, refined and augmented through one's own life's work, continues to illuminate the minds of those who follow. Pisharati's answer to this perennial question of intellectual inheritance would become his most profound and lasting contribution. His genius for mentorship is most vividly illustrated in his relationship with his celebrated student, Melpathu Narayana Bhattacharyya. Bhattacharyya was a prodigious intellect in his own right, a poet, grammarian and philosopher whose talents were recognized from a young age. Under Pisharati's tutelage, he absorbed the full depth of the Kerala school's astronomical and mathematical knowledge. The bond between them was famously deep, a connection that transcended mere academic instruction. A compelling, though perhaps apocryphal, story from the tradition speaks to this bond's intensity. When Bhattacharyya was struck by a severe ailment, Pisharati is said to have, through a yogic or spiritual process, taken the affliction upon himself to free his brilliant student to continue his work. While the literal truth of this event remains in the realm of hagiography, its metaphorical power is immense. It speaks to a conception of teaching as an act of profound self-giving, where the guru's ultimate purpose is the flourishing of the disciple, even at great personal cost. Freed from his illness, Bhattacharyya went on to compose his magnum opus, the Narayansya, a masterful Sanskrit poem of 1,000 verses summarizing the stories of the Bhagavata Purana. While a devotional work, it is universally acclaimed for its linguistic perfection, its metrical precision, and its dense, scholarly allusions, all hallmarks of the rigorous intellectual discipline instilled in him by Pisharati. The work stands as a monument to a mind trained in the arts of precision and synthesis. Bhattacharyya also authored important treatises on grammar and, crucially, composed astronomical texts like the Praya Sarvasva, which directly continued the computational and theoretical work of his master. Through Bhattacharyya, Pisharati's legacy was secured. The complex web of infinite series, iterative algorithms, and refined planetary models passed from one great mind to another, ensuring the flame of the Kerala school would burn for at least another generation. Pisharati's own writings, particularly the Karanotama, can be seen as instruments of this pedagogical project. By creating a clear, concise and practical handbook, he was building a bridge for future students. He was taking the towering intellectual edifices of Madhava, Nilakantha and Jayastadeva and creating a functional entryway. The text was a tool designed for use, a way to make the power of the tradition's insights accessible without requiring every practitioner to rederive the entire theoretical foundation from first principles. This act of codification and simplification is a hallmark of a mature scientific tradition, and in Pisharati, the Kerala school found its great synthesizer and its most effective disseminator. He consolidated the revolutionary discoveries of his predecessors and packaged them in a form that was robust, usable, and most importantly, teachable. His life's work represents the magnificent twilight of this unique intellectual ecosystem. He stands as arguably the last of the great luminaries in a continuous line of astronomer mathematicians stretching back to the 14th century. The world around the Kerala school was changing. The political landscape of southern India was becoming increasingly fragmented, and the arrival of European mercantile and colonial powers introduced new cultural and economic pressures. The traditional systems of patronage and the quiet, cloistered environments that had allowed this specialized knowledge to flourish for centuries were beginning to erode. Pisharati's students, like Bata theory, carried the tradition forward, but the singular conditions that produced the school's golden age were fading. His career thus marks a culmination, a final brilliant synthesis of the school's achievements before its gradual diffusion and decline. To reflect on Achyuta Pisharati is to contemplate the very shape of the history of science. For centuries, that history was written as a singular, linear narrative, a relay race in which the baton was passed from the Greeks to the Islamic world, and then to Renaissance Europe, where the scientific revolution ignited. The story of the Kerala school, and Pisharati's place within it, profoundly challenges this simple chronology. Here was a community of scholars, working in relative isolation from the intellectual centers of Europe, who independently developed the conceptual tools of calculus, infinite series for trigonometric functions, terms of integration, and a sophisticated understanding of approximation and error, all centuries before Leibniz and Newton. The existence of this parallel trajectory of discovery invites a more pluralistic and global understanding of scientific history. It compels us to see the development of mathematical thought as a process that can occur in multiple cultural contexts, driven by its own internal questions and intellectual imperatives. The astronomical problems that animated Pisharati and his forebears, predicting eclipses and modeling planetary motion, were universal. Their solutions, however, were uniquely their own, born of a distinct philosophical and mathematical heritage. Pisharati's legacy, therefore, is twofold. Within the context of Indian intellectual history, he is the masterful guru who consolidated and ensured the transmission of one of its most remarkable scientific achievements. In the broader context of world history, his work and the tradition he represents serve as a powerful corrective. They remind us that the quest to understand the cosmos through the elegant language of mathematics is a deeply human endeavor, one that has unfolded in many places and in many voices. Achyuta Pisharati stands as a testament to a magnificent flowering of human intellect, a final brilliant star in a constellation of genius that charted the heavens and explored the infinite from the shores of Malabar. His life was a quiet testament to the idea that the universe reveals its mathematical secrets to anyone who has the patience, the ingenuity, and the courage to ask the right questions.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.